Our IWCS webinar series event is hosted by the International Cable and Connectivity Symposium. I am Ed Fenton, a cable industry advisor working with the IWCS team. As Connie said, if you have questions, please use the Q&A box on the bottom right of your screen to post a question anonymously. If you wish to contact the presenter or IWCS after the presentation, you will be given the contact points at the end of the webinar. Please note that IWCS does not distribute the presentation slides from either of our conference sessions or these webinars. However, please feel free to contact the presenter directly, and they will respond individually to you. Today, we welcome James Henry, Principal Research Engineer, Arkema, Inc., King of Prussia, Pennsylvania, USA, who will be presenting his paper on high-performance polymers in wire and cable. James Henry is a Principal Research Engineer, Arkema, Inc., located at the Research Center in King of Prussia, PA. James received a bachelor's degree of chemical engineering in 1986 from the University of Lowell and his master's degree in plastics engineering in 2003 from the University of Massachusetts. Jim joined Arkema, Inc., formerly Adafina Chemicals, in January 2001, where he focuses his attentions on activities in the wire and cable and chemical processing markets. James, we welcome you to present at today's IWCS webinar series event.
Great. Thank you very much, Ed. Greatly appreciate that introduction. Just give me 1 second. Okay, very good. First of all, thank you everybody today for joining today's webinar. The title of the paper that accompanies this presentation is called High Performance Polymers and Wire and Cable. I recently gave this presentation at IWCS in Orlando back a couple of weeks ago. As the title suggests, today's presentation will cover topics related to the use of materials that can provide targeted performance and sometimes extreme performance for wire and cable applications having different attributes. Start, Arkema today is a $7.7 billion company. We have 19,000 employees worldwide, and we are present in 50 different countries. We have 136 industrial sites and 3 R&D centers. The 3 centers are located in Sourdato, France, Changshu, China, and KOP, which is where I reside at this point. We also have facilities in Seoul and Kyoto. At Arkema, our primary focus is high-performance materials. We look at specialty adhesives, performance additives, and in this case, for this presentation, it's going to be technical polymers. There are many different characteristics associated with high-performance polymers, and they can be defined in many different ways. In this particular case, in our presentation, I looked at high-performance polymers as a material that's capable of providing some sort of benefit that other materials that are more commonly used might not be able to provide. Things such as looking at the left-hand side, we have high thermal stability. This is a very common attribute, and what's more important is not just high thermal stability, but also high thermal stability and retaining, physical and mechanical properties. There's also high resistance to chemicals, and oftentimes that high resistance is also associated with chemicals at elevated temperature. The other issues that are of concern is the range of physical and mechanical properties. We have materials that require flexibility or rigidity, and they have to be able to maintain these properties at elevated temperatures. There's other properties as well that would also be considered high performance. They might include abrasion resistance, UV resistance, nuclear resistance, and in the wire and cable industry, one of the very common high-performance characteristic is related to good flame and smoke properties. There's a number of different cable applications that use high-performance materials. Examples would include heat shrink tubing, which might require high temperature or chemical resistance. Indoor-outdoor fiber optic cables would be another good example. These are cables that would require outdoor exposure as well as indoor exposure and plenum application. And so you would have a unique set of requirements to be able to handle all of that. Cathodic protection cable, that would be cables that require that are used in brackish waters and require very good permeation and chemical resistance. Just looking over on the far right-hand side of this table, you have shipboard cables, military and defense, downhole mining cables. All of these types of applications require a whole series of performance characteristics, including high temperature, chemical resistance, and a wide range of physical and mechanical properties. There's many examples of high-performance polymers. For this particular paper, I listed 5, and in this presentation, I'm going to talk about 4. Starting on the left-hand side, I'm going to talk a little bit about fluoropolymers, and as most people know, fluoropolymers provide good chemical resistance, flame and smoke resistance, durability. But in this presentation, we're going to talk about PVDF and PVDF copolymers, which also provide ease of processing. There's also many different types of alloys that are used out there in industry. We're going to talk a little bit about one type of alloy, and that's polyamide polyolefin alloys, and the benefits of their high performance to cost ratio. Another area we're going to talk about is grafted polyolefins, which again, there's many. But in this case, we're going to talk about polyamide grafted polyolefins, okay, and the benefits of having a combination of these two particular products. Lastly, we're going to talk a little bit about polyamides, and again, polyamides are used quite commonly in the wire and cable industry. They offer a very wide range of properties, but in this case, we're going to talk about long-chain polyamides, and specifically some of the properties that you will see improved using these particular types of polyamides. Okay, starting with PVDF and PVDF copolymers. Okay. This particular chart was put together just simply to talk or explain a little bit about the performance characteristics of fluoropolymers. Fluoropolymers in general provide good chemical resistance, good insulation properties, good moisture absorption, and flame and smoke is always, very good as a class for these grades. The specific material we'll be talking about, which is PVDF copolymers, their temperature resistance is not as good as the other fluoropolymers. Okay, that's a benefit. Disadvantage in some cases, a benefit in another. One of the benefits of having a lower melting point is processability. These PVDF, HFP, and PVDF copolymers in general are very easy to process, and they can be processed on conventional pieces of equipment. The other areas that PVDF resins excel in is in abrasion resistance, and they offer a wide range of flexibilities. Again, what I have here on this slide is we're looking at different fluoropolymers on the left, and we're looking at the flexural modulus of these products. Starting down below, we have the fully fluorinated polymers. These products are well known for their chemical and temperature resistance. They tend to be relatively soft, and they're used quite commonly for wire and cable applications. The other types of fluoropolymers are sometimes referred to as partially fluorinated polymers. Usually some of the fluorine is replaced with chlorine or hydrogen. And those products tend to provide a much stiffer characteristics. PVDF copolymers as a class are very useful because you can get a wide range of properties. This range of properties is gained by varying the amount of comonomer. So if you have no comonomer, you can have a very rigid product used for pipes, molding, all different types of structural applications. And with very high comonomer contents, you can have very, very soft and very flexible products, very useful for wire and cable. Making a PVDF resin, it starts with a mineral called fluorspar. The fluorspar is where the fluorine comes from. The fluorspar is reacted to produce HF. The HF is used to produce fluorinated monomers, and those monomers are reacted to produce fluoropolymers. For PVDF resins, they tend to come in 3 forms. They can come in a powder, a pellet, or a latex. PVDF resin is a very simple polymer. It's a linear carbon chain with alternating fluorine and hydrogen. Okay, and it's very highly crystalline, which lends itself to its good properties. Copolymers, there's a number of copolymers that can be used. CTFE is one. HFP is another. In this case, HFP is being used, which is hexafluoropropene. And the way it works is you have this fluorinated pendant group that is introduced. This pendant group interferes with crystallinity, making the product softer. Before I get into the details, I want to talk a little bit about safety with running fluoropolymers. One of the benefits of PVDF HFP copolymers is that they tend to be fairly safe compared to other fluoropolymers to process. And when I say that, what I mean is the decomposition profile and the actual process temperatures are quite, the range is quite large. In this TGA, which shows weight loss as a function of temperature, what you see here for this PVDF homopolymer, you see decomposition onset starting at around 410 degrees C. Typical melt processing is usually 210 to 240, with wiring cable usually be on the higher side. As you'll notice, this temperature is significantly below the decomposition temperature of the product. Other attributes worth noting is PVDF has a very high LOI, but in the wire and cable industry, we often add materials, we call them flame retardants, to the product, which actually raise the LOI to values above 95. So this makes these products very useful for plenum applications. All right, now on to something actually a lot more interesting. We're going to talk a little bit about heterogeneous PVDF HFP copolymers, so some of the newer products that are available. Heterogeneous, what that means is that we have a material that is two-phase in the solid state, usually a rigid phase and a rubber phase. In 2 slides from now, I'm going to explain that a little bit further. But some of these products, new products that are available, what they provide is very wide ranges in flexibility down to 200 megapascals. And most importantly, they offer very good low temperature impact performance. Our target when we started developing these products was to get down below -10 degrees. We have several products. There's several products out there that are below -25, and there are now some that are well below -40 degrees C for very low temperature applications. All of these products are 150 degrees C rated, good for indoor-outdoor fiber optic, and also for outdoor applications requiring cold temperature performance. Okay. This is a very useful slide for trying to understand the different grades and ranges of PVDF HFP copolymers. What we have is we have melting point. What's missing here is a description down below, and what that should be is flexural modulus, which is in kPSI. And so looking at the bottom axis, on the far right are rigid materials, and the far left are flexible materials. Coming up to this green arrow, what we know is that as we increase our copolymer content, we produce softer and softer products. The first type of product I want to talk about are homogeneous PVDF HFP copolymers. What we know with homogeneous products, where the copolymer is uniformly distributed, as the amount of HFP increases, the product gets softer, but the melting point also becomes depressed. This limits its use from being used at higher temperature applications, but some of the benefits are that these products are very, very easy to process, and they tend to have very low shrink back. The newer materials are heterogeneous in nature. The benefits with these heterogeneous structures is that they provide high melting point, so they're inherently rated for 150 degrees C, but they also have very good low temperature properties as well too. And there's a wide range of flexibilities that are available. Okay. On this particular slide, we're looking at some SEM images of different heterogeneous structures that can be produced by combining PVDF and HFP in different ways. On the left, we see more of a discrete rubber phase, where what we have here is we have a sea of homopolymer, and then we have these discrete rubber phases where are very high in HFP. They act as an impact modifier in the product itself. Through changing the recipe and the conditions and how it's put together, we can change the structure of this heterogeneous nature. We can make the rubber phases larger. we can actually have them interconnect and create interpenetrating networks. And as you would expect, in all of these cases, the physical mechanical properties are going to vary, as well as chemical properties as well, based on how you decide to build this material. For these products to be useful, you need to have a stable morphology, which in this particular case, these products can be extruded over and over again without having any loss or effects on the morphology of the product. Okay, there we go. This right here is a DMA, and I apologize if I can't explain I'm not going to be able to, don't have time to explain all the details of the information that's provided here, which is quite a bit. And I'm going to focus on these two curves, which shows the tan delta. And the tan delta is often used to understand the transitions and try to predict where, most of the time, where ductile brittle transitions may occur. In this particular case, the black line is a homogeneous PVDF copolymer, and the silver line is a heterogeneous product. And we combined it in such a way that you can see that the tan delta has shifted. Now, in this particular region, down around -40, -50, that is the traditional glass transition temperature reported for PVDF resins. So we see a subtle shift in that T sub G. So we know that this silver heterogeneous product is going to perform better at low temperature. Of more importance, though, is this secondary transition, which often is not reported. This transition is what controls low temperature impact. And in this case, by making this heterogeneous product, we can get down to about a -30 degrees C impact. The low temperature T sub G, I'll point this out, usually controls slower processes such as like low temperature mandrel wrap, and usually that would be an indication that these products would perform very well down to -50 degrees C for those sort of tests. Okay. This is just a comparison of a homogeneous to a heterogeneous product, looking at some key properties. What we're dealing with is two products that have the exact same amount of HFP and the exact same viscosity. Of importance, the heterogeneous product provides a much higher melting point. The physical mechanical properties tend to be very similar. In general, though, we do find that the heterogeneous products do tend to have higher elongation at break, and they tend to be a little bit more ductile. And most important, the ductile brittle transition temperature is significantly reduced, and in this case, down to about -25 degrees C. Then for other products, we have products that go down to -40 degrees C, and in this case, comparing two heterogeneous products, one having our standard package and another one our enhanced package, we have very similar properties, but we were able to get the low temperature performance down to -40, -50 degrees, which is very significant. Okay. One of the other areas that we've been working on is improving crosslink efficiency. PVDF polymers in general are used very commonly for producing heat shrink tubing and also for higher temperature rated cables, maybe automotive cables, transit cables, rated up to 175 degrees C. For those not familiar with cross-linking of PVDF resins, normally a promoter such as TAIC, which is triallyl isocyanurate, is normally used as a cross-linking agent. E-beam dosages of 6 to 10 megarads would be typical. And, there's always a desire to reduce the amount of radiation dosage because it does affect color, and higher dosage can cause reduction in crystallinity, lower thermal stabilities, and change scission. So there is a benefit to the industry of having products that perform better. This can be a hard slide to try to explain, and I'm going to do my very best. What we're comparing here, this is viscosity as a function of shear rate, and I'm comparing two products. The lines in red are a commercial product, and the lines in blue are a DeVental improved cross-linkable grade. The red grade is what I would consider a preferred or one of the best or premier products out in the market, and the blue is something we're working on to try to improve that. The samples were radiated. You had your baseline, plus they were radiated at either 3 or 6 megarads. And the basic properties of the two products were similar. What I'll compare here is looking at the two products that has no radiation, you can see that the viscosity is pretty much identical. However, when we go to 3 megarads of radiation, which are these lines with the circles, I'll be comparing the red line here with the blue line right here. What we see is that the blue line is higher, which means that it has a higher viscosity and that it cross-linked more efficiently at 3 megarads. And then at 6 megarads, where there's a triangle, you can't see it, but it's underneath for the red, and a triangle for the blue, you can see that at 6 megarads, the new copolymer and cross-links a little bit better. And a nice, easy way to describe this, though, is looking at the overlap here. It's saying that with the new polymer, I can get, at 3 megarads of radiation, I can get the same cross-linking as 6 megarads with the existing products. So that's a significant reduction in the E-beam intensity to get the same performance characteristics. Okay. Another area that's really interesting, and we've and actually I'm very excited about, is the developments in foamable PVDF technology. It's been out there for some time. The traditional technologies can be very difficult to use. If done properly, it's actually not that difficult. But what I found is that trying to do it consistently and without any processing type of problems can sometimes be difficult. Well, there are new developments that are going on with foaming technology that eliminate these process-related problems that affect startup and increase scrap rate. And not only that, but are able to get foam reductions actually 65, 70% very consistently. And it's controlled simply by the addition of the concentrate independent of processing conditions. What's exciting about some of these new technologies is that we're seeing extremely good plenum performance. We were able to, there was materials that were taken that had a 65% weight reduction, and we're able to get a 0-0 in a Steiner tunnel test, a UL 2020 test. This is a very exciting area. There's still work that needs to be done. That will be done over the next several months, but I expect that this is going to be a very useful product for wiring cable in the future. Next area I'd like to speak about are polyamide alloys. The polyamide alloys that we see, normally if you blended polyamide and polyethylene, you would not see any compatibility. The polyamide are these spheres. As you can see, there's no compatibility. You add a compatibilizing agent, the two products become miscible, and they start having very useful properties. One of the most important properties that you gain is chemical resistance. Okay, these polyamide polyolefin alloys, they have very, very good chemical resistance compared to the products that they might replace, such as Crosslink PE, PE, and PVC. They have low density, they have thermal resistance, their chemical and barrier properties are exceptional. This is where the nylon actually becomes very dominant in its properties, whereas the presence of the polyolefin reduces its moisture uptake. The other characteristic of these products are that they're very easy to process. And one other slide I'll present on these polyamide polyolefin alloys is just related to moisture absorption, and in this case it's expressed as flexural modulus and its effects from water exposure, where these first two materials, what we see is that after exposure in water for 40 days, you have some reduction in flexural modulus, but it's reasonable. It's relatively low. Whereas compared to other polyamide products, which have much higher moisture absorption, you're going to have a much more significant drop in flexural modulus properties. Next, we're going to talk about polyamide grafted polyolefins. These are very interesting products. They are similar to what I was just talking about in the sense that they contain polyolefin and polyamide, but how they're put together is quite different. In a grafted polyolefin, what we have here is we have a polyolefin backbone, and we have the polyamide grafted directly onto this polyolefin backbone. Okay, it creates a very unique structure, and this is what provides a lot of the beneficial properties. Looking over here at a TEM image of one of these grafted copolymers, what we see is we see phase separation, where the matrix itself is the polyolefin, and what looks like these small sea worm-like creatures that exist in this background, that's the polyamides segregating. It's a co-continuous phase, and this morphology actually provides a very useful set of performance characteristics for multiple applications, including wire and cable. The natural resin itself is transparent because of we'll say the size of the structure is extremely small. What I have here is this is a DMA of different products, and what we have is various levels of polyamide. Okay, the DMA we have, looking at the characteristic DMA, we have the softening of the polyolefin, which is occurring at these temperatures, and then we have the softening of the polyamide that's included in the structure. These different lines represent different levels of polyamide, where down here this is low level of polyamide and this is a high level of polyamide. And what we learn here is that the melting point is independent of the amount of polyamide, and that by raising the amount of polyamide you can get a product that maintains its structural properties over a very wide temperature range. One of the other benefits of these grafted polyolefins is their thermal resistance. 3,000 hours test at 150 degrees C saw a relatively minor drop in elongational properties. Starting over here on the left at 150 degrees C, what we see here is that the product itself, which is we're measuring elongation, you do have a drop in elongation, and then it levels out with a 30% drop in ultimate elongation that looks like it pretty much extends and continues after 3,000 hours. Short-term exposure at 175 and 200 degrees C is also could be handled with these resins, where you can see that the elongational properties, that 50% of the elongational properties are still retained after 300 hours at 175 degrees C. Okay. The area that I see these materials being used is in HFFR applications. Okay. The primary benefit here is that you have a good balance of properties. We have very low temperature, very high elongations, and what's important here is that the continuous use temperature of 150 degrees C without any cross-linking can be attained with these particular materials. The PO backbone, the polyolefin backbone, provides good processing, and it has very favorable characteristics. This over on the right, this was a test. It was 300 hours at 175 degrees C, and after winding at minus 25 degrees C, we see no cracks. So the overall properties are very, very good. And because it contains a polyamide, nitrogen-based flame retardants are found useful in this product. Okay, and so we're able to get a V0 rating fairly easily by using standard polyamide type flame retardants. The LOI is very high on this product, which is 36% or more, meets the HFFR requirements. The only thing I'll note is the addition of flame retardants obviously will make the product opaque in the end. The last area I'll be covering is long-chain polyamides. Long-chain polyamides gain their properties from hydrogen bonding of the amide group, and the properties of individual polyamides vary based on the number of carbon chains that separate these polyamide linkages. Looking over here on the left, you can divide the different types of polyamides into those that use fossil fuels and to those that use renewable resources, such as castor beans. And then we show a performance pyramid where at the top we have the best performing products. For these materials at the top, which tend to be our long-chain polyamides, they provide chemical resistance, low moisture absorption, lightness, and what I'll explain is good low temperature impact, good impact properties. The short-chain products, due to the higher amount of amide linkages, will have higher crystallinity and provide better fuel resistance and thermal resistance. This slide is a very interesting slide which shows the polyamide types. And what I'll say is, I'll briefly explain what is in here. What we have is the long-chain polyamides on the right, short-chain on the left. As you would expect, as you go from high to low, the hydrogen bonding increases, crystallinity increases. And then for properties, as you would expect, as crystallinity increases, the density also increases, melting point increases, tensile strength increases. Elongation of break, as you would expect, softer products, you're going to have a much higher elongation of break for 11 and 12. And what's important is you'll also have lower moisture absorption. Water absorption on the long-chain polyamides, we're looking at 50 and 100% relative humidity. What you can see is that these long-chain polyamides have very, very low moisture absorption compared to other polyamides. And so in this case, the water absorption is maintained at 50% RH, well below 1. But another way of showing this would be looking at the flexural properties. And this is comparing long-chain polyamides on the right to shorter chain on the left. And what you see here is that going from a dry to a humid condition, the long-chain polyamides don't change that much in flexural properties, whereas the shorter chain, because of water absorption, will have significant property changes relative to moisture absorption. One of the most important benefits of PA11 specifically is its higher impact strength compared to all the other polyamides. Polyamide 12 is by itself very good impact, having performance similar to polycarbonate. But polyamide 11 is significantly higher than that, having impact strength greater than 50 kilojoules per meter squared. And this slide right here on the left kind of explains, part of the reason why. What we see is that for PA11, if you're looking at tensile properties, during the neck-down process, it takes much more energy to reorganize the crystal structure in that polymer than, say, PA12. And if you look over here on the right, you'll see that the crystal structures are different. And with PA11, reorganization of these ring spherulites takes much more energy than the coarse spherulites. And this gives the different tensile properties and, more importantly, the improvements in impact. This last slide, I threw this in just for general information. It's comparing PA11 and PA12. And all I want to point out here on this slide is this particular thermal transition, the low temperature, which controls low temperature properties. PA11 is a little bit better than PA12, and you probably get another 5 or 10 degrees C of performance if you needed it at those low temperatures. So in conclusion, these high-performance polymers have been used in wire and cable industry for many years. They offer great physical, mechanical properties depending on the applications, temperature, chemical resistance, oxidation resistance, hydrolytic stability, a wide range of properties that are useful for wire and cable, and low flame and smoke characteristics. And so the products that I discussed today, they are being used in the wire and cable application, and we continue to produce new products to solve new problems and to improve upon what has been used for many years. And with that, that is the end of my presentation.
Thank you, James. At this time, we will ask as many questions from the attendees as time permits, starting with this first question. Are PVDF copolymers functional as a jacket in data communications cables, or can they be functional as audiovisual signaling or security cables?
Okay. First of all, PVDF and PVDF copolymers are used quite commonly as jackets, okay, in many different applications. Quite often in plenum, often used in transit and other applications. One aspect of PVDF resins is that they have a high dielectric constant and a high dissipation factor. So that limits its use in certain data communication applications. In a shielded construction, they're often used as jackets, but in high-speed data communication, direct contact with the conductor or that's transmitting is not acceptable due to high losses.
Okay, thank you. Next, have you evaluated these materials in cables that carry both power and data?
Actually, in some of the new cable constructions, power over Ethernet, we've not done any work in that particular area. What I can tell you is that these products, the PVDF resins specifically, I'll talk about them, are used in power cables. They're also used in low voltage. They're used in fiber optics, and they're used individually in those applications. A lot of the limitation that you might have depends on the temperature environment, where these materials are only rated to 150 degrees C, and so if you need higher temperature ratings, they might not perform adequately. So that would be one of the limitations that would prevent wider use in this gentleman's question.
Thank you. Does foaming improve any other characteristics of high-performance polymers in addition to flame and smoke?
Excellent question. They're all excellent questions, by the way, but that one's really interesting in that what we see is that you get added flexibility. Our experience has been that the shrink back is actually reduced with these foamed products. That's very important in data communication. If strippability is an issue, they tend to be more strippable. And most often, flexibility tends to be what also provides a benefit. And I think the other benefit is if you can get a 65% reduction in the weight, there's a significant cost benefit as well too.
Okay, thank you. With the enhanced smoke and flammability of the PVDF materials through foaming, can these materials be applied into fiber optic cables, considering potential problems related to moisture accumulation?
Well, first of all, I suspect yes. These products are new, so I can't say that we have any examples that I can give you that to express whether they can or can't. The kiner itself, though, is still the majority of the product and is very hydrophobic. So I would suspect that these products will work extremely well. There's no plasticizers or anything else that would tend to absorb moisture, and so I would suspect that these foams are going to behave very similar to the natural products.
Okay, thank you. How do polyamide grafted chains affect the dielectric performance of the polyolefin? Are these materials used primarily for insulation or jackets?
That's a good question. I don't have any data for that particular question. I would highly recommend that that person give me a call after this presentation. What I can say is that the addition of polyamide does increase its moisture absorption, so that you're going to have some higher moisture absorption compared to just polyolefin. But with that said, it's relatively small. So what I would say is please have this gentleman give me a call after, and we can talk further.
Okay. Can you comment on the transparency and resistance to yellowing with heat? For example, 85 degrees C for 1,000 hours of PVDF.
Well, it really depends on the product itself. And the resin that you're using. Okay, on a base resin tends to have fairly good color retention, But anyone who's ever processed PVDF will know that that the product does yellow with each individual processing. When you get into plenum grades, color shift tends to be extremely low at very low times, and then it starts increasing at extended times. When you get into cross-linking, the color retention becomes very poor. Okay, where the product itself becomes very sensitive to color shifts after the radiation process.
Thank you. Next question. Is radiation the only way to cross-link PVDF?
Well, actually, no. There's always the ability to functionalize PVDF resins to be able to cross-link using other types or other methods. But it is currently the only way that is currently used to cross-link, and the reason why is that it is so easy to it cross-links very efficiently by E-beam exposure. So right now, it's really the only practical way that's currently being used.
Okay. Next, what is the UV resistance of PA grafted polyolefins?
UV resistance of PA grafted polyolefins. I think that is another question I'm probably going to have to ask the gentleman to give me a call directly. Okay, I know it varies with individual grade, and I think I'm going to have to probably do a little bit of digging to answer that question.
Okay. Enough said. Next question. Is foaming of PVDF with a physical nucleating agent and injected gas or chemical foaming?
It's a chemical foaming.
Yeah, chemical foaming.
Yep.
Okay.
The foaming agent would be added just like a concentrate, but it uses some more advanced technologies that really separate the processing characteristics that normal foaming tends to need to be able to get a uniform structure, whereas these new products tend to be independent of processing, and they foam more consistently.
Thank you. Next, what changes are expected to have in machine process between current PVDF and the new foaming version of it?
That's a really good question. Significant. There is a difference. Okay, the foam foams at 65% tend to have lower melt strength. Okay, and so what you have to do is you do have to drop the drawdown ratio to be able to process these. Usual kind of resins PVDF resins can range from drawdown ratios between 3 and 10, depending on the grade. Whereas the foams will probably require drawdown ratios around 2. So it probably will reduce line speeds. The other aspect of these foams is it's very difficult to get a smooth surface. And so applications that require a very smooth surface would not be able to be foamed. Other than that, though, they tend to be very friendly.
Okay, thank you.
Mm-hmm.
At this point, we're going to move into conclusion. Thank you, James, for presenting this very interesting and important topic today. Please note the contact points being shown should you wish to contact James after today's event. Each of these IWCS webinar series presentation events are recorded and will be archived on the IWCS.org website. It normally takes up to 2 weeks for these to be posted. The IWCS webinar series will conduct presentation events on a monthly basis. Webinar events will take place on the third Friday of each month at 10:30 a.m. Eastern USA time. Our next scheduled event will be on Friday, November 17th at 10:30 a.m. Eastern USA time. Each of you will be receiving an announcement for the event a few weeks prior. Please feel free to share our announcements with your colleagues so that they can join in and register as well. For over 65 years, the IWCS International Cable and Connectivity Symposium has been the recognized leader showcasing new technologies in cable and connectivity products, processes, and applications. Our next annual international conference will take place on Sunday, October 14th through Wednesday, October 17th, 2018, at the Rhode Island Convention Center in Providence, Rhode Island, USA. In addition, our second annual regional UL and IWCS China 2018 Cable and Connectivity Symposium will take place on Tuesday, March 20th through Thursday, March 22nd, 2018, at the Shanghai International Convention Center in Pudong, China. Please visit our website at iwcs.org for more event details. In just a moment, you will see a brief survey so that you can provide us your feedback and comments on today's event so that we can further improve this webinar series for you. Thank you for participating, and this concludes today's event.